We good? All right. Okay, so we got a new memory card. Anyway, so after that, we figured out 1/4 is the identity in this algebra. So we are supposed to take, like, if this is algebratizable, and this is its algebraification, if you will, then that would mean that if we take this and put t times the identity, then it should serve as a solution to the original problem. So that means I still need to calculate -1 over some constant plus t times this guy. Now he has formulas. All right. He has formulas, and he claims that this gives us x1 of t, x2 of t equal to something along the lines of minus t minus b over 4 times 2t plus a plus b squared, comma, minus t minus b over 4 times 2t plus a plus b quantity squared, where x1 of 0, y1, or x2 of 0 rather, is equal to minus b comma a divided by 4 times a plus b quantity squared. Interesting. So at the moment in our discussion, I haven't really explained to you how on earth it is we got from here to here. But I think you can kind of start to see it if you just look at this right here, right? What happens if we put x1, x2, and just suppose that these are equal to x1 and x2 like that, right? Then we get 3x1 squared, and here we get what? x1, x2. So we get, what do we get here? I guess we get, how do we get 2? I don't see how to get the, oh, that gives me the minus x2 squared. Oh, I'm sorry. Yeah, duh. So this and this give that. This is that, and this one is that one. And then likewise here, I see. So it's pretty manifest that when I take that pair together, it becomes d zeta d tau, like that. So it seems like the modus operandi, if you will, is something like this: dr. So if we have dr dt, right, that's going to transmorph into something like d zeta d tau, right? And then over here, you pick up if you can arrange the components on the other side such that they're equal to your favorite, h of zeta, right? If you can arrange those to identify those as h of zeta, then it's algebratizable. And I would wager that the solutions to the algebra equation then so that's just my, I've not proved that. That's kind of what I'm seeing here from a just quick look at it. Neat. Okay, so Anyway, I've got tons more to learn about that paper. I'm just starting, but I'm excited because it's a different way to think about A calculus. It's a new thing for me to think about it in terms as being the study of vector fields. I mean, that's not something that had occurred to me. I was thinking partial differential equations. It's about partial differential equations, right? But, you know, if I had thought about it some more, I should have not been surprised by this, because there's always this interplay between partial differential equations and the so-called characteristic vector fields that underlie them. And we can always, you know, the whole study of Lie symmetries and all this sort of thing involves this interplay between vector fields, PDEs, and first-order differential equations. They're all kind of different sides of the same math. Okay, so my third paper, right? The third paper with Nathan Bedell, right? Who, by the way, is now at Tulane, studying things that don't look anything like what we're doing. He's one of these category theory peoples, but I paid him enough money to make him think about A calculus for a few months, and I got some good results out of him. So I'm pretty happy. It was good money well invested. It was my wife's ill-gotten money, but this is not really my money. But anyway, I had the pleasure of working with Nathan over the summer. And so I've been thinking about these questions before then. For example, the inverse problem I'd worked on with Beilu Zhang for months on end, and we got somewhere. We thought we had something, but then the summer 16, Nathan showed me that I had done two things. On the one hand, I had distinguished algebras as isomorphic algebras as being distinct, but at the same time, in the same breath, I was working up to isomorphism. So, like, you can't have your isomorphism and not have it too. Like, so long story short, I had found a way to confuse myself and Beilu too. And our calculations, while to me still very interesting, don't mean anything directly. And the trouble is, what I thought was a two-dimensional problem was actually a four-dimensional problem. So all of our happy two-dimensional classification results are just nonsense. And so that kind of shot the summer 15, like the penultimate thing I found in summer 15 is kind of not where it needs to be yet to publish anywhere or anything. I don't even understand it entirely yet. But I know eventually I'll go back to what I did with Beilu, and it'll be part of that larger story. But that's down the road. So Nathan, though, I just presented, I mean, our basic task was, can we solve differential equations over an algebra? The question is, can we solve the differential equations over an algebra which are straight analogous to just ordinary differential equations class? Like, what do you study in ordinary differential equations? First order problem, right? Integrating factor technique, exact equations, separation of variables, all that stuff, the existence uniqueness theorem, and then what's the next thing you do? Higher order differential equations, right? Factorization of operators, or the complexification technique. And then what's at the end is systems of differential equations. After that, you know, can we solve systems of A differential equations? And Nathan made substantial contributions to all of those. I'm still not done with systems. Kang and I have worked on that some, but we're still, it's in process. I mean, we found some really, really bizarre examples, which we'll show you guys later, but not yet. First, though, we should just try to understand just the basic thing. So, you know, first of all, just first-order problems. First-order AODEs, as I call them. For me, an AODE is just a differential equation over the algebra. So something like, and so I won't. My example is not so interesting as this one. But this is the, Beilu gave this in a talk at Longwood, I think in 2014. So I've known about this for a while. Just, you know, if we look at the hyperbolic numbers, we can look at the differential equation dw dz equal to z squared, right? And it's easy to check that w equal to minus 1 over z plus a constant solves it. Now, I know that that's going to work because I did separation of variables. I mean, I isolated and integrated. That's the man behind the curtain here is one we all know and love. This is dw. Oh, you guys are confused with good reason. That's supposed to be a w squared. So, we got dw over w squared equals dz, and then integrating gives me that. We'll integrate and then solve for w. But the thing that's neat is that this is really u plus jv equals to minus 1 over, well, x plus jy, right, plus a plus jb, right? And since this is hyperbolic numbers, I don't have to really sweat it that much. I know how to reciprocate by multiplying by the conjugate, So I just multiply by x plus a minus j times y plus b divided by x plus a minus j times y plus b. And out pops my minus x plus a plus j times y plus b divided by x plus a squared minus y plus b squared. So, great. That suggests to me that u is minus x plus a divided by x plus a squared minus y plus b squared, and v is y plus b over x plus a squared minus y plus b squared. Now, I did something that I should never do. I showed you the man behind the curtain. I showed you my technique. The proper way to do this to wow people is I start with the partial differential equations, and then I change to the algebra equation, and then you're like, whoa. You see, I've done things backwards as to not impress you. But if you look at this, what does this actually mean? Well, remember that if we're looking for h differentiable functions, dw dz is really just partial xw, right? Because those are the Cauchy-Riemann equations. The Cauchy-Riemann equations are most aptly and elegantly summarized by just saying this. But that's a lie. I mean, generally speaking, you would build partial x. I mean, that's not the whole story, right? I mean, that equation is only true for h differentiable functions. If you want me to write an operator equation, partial z is actually like, what is it? It's like 1/2 partial x minus j partial y, something like that. If you want to write it for arbitrary functions in the plane rewritten in terms of hyperbolic variables. That's that conjugate calculus stuff I showed you guys ever so briefly in here. But anyway, so this is what? Well, this is nothing more than partial x of u plus jv equals to u plus jv squared. And you see what I've actually solved is partial u partial x equal to u squared plus v squared, and partial v partial x equal to 2uv, subject to the other equations, of course, namely that partial u partial x equals partial v partial y, and partial u partial y equal to partial v partial x, right? I mean, I've got all of these. This system of 4 partial differential equations, 2 of which are coupled and nonlinear, I solved by a second semester calculus technique, separation of variables, in the algebra. So for maximum effect, I really should start with this, pull the hyperbolic numbers from the thin air, and go, look at this, right? That's the smart way to present this example. See, smart. So that's a first order. So first order differential equations, we can solve just like you do in differential equations. Separate, integrate. You can look for integrating factors, the rest of it. The part that I've grown to love the most is the higher order differential equation problem. So let's try to look at a non-trivial one, something where we get into trouble. Let's see here. I think even this one is enough, something like this. Suppose you wanted to solve w prime prime minus w equal to 0. I think we've gotten a lot of insight just from this example. Right? And I want to solve over the hyperbolic numbers, right? So how would you, what technique, how do you do this? How do you do this in differential equations? What do? You write down the characteristic equation, you factor it, and you use the factorization to just, So what's the characteristic equation here? The characteristic, so Jess, we're moving on to second order problems. I'm trying to introduce some of the wrinkles into solving differential equations over an algebra. The end of this story is good, though. Basically, everything that you learn in the ordinary course, modulo, I still don't know about Fourier techniques. I don't know about Laplace transforms. There are techniques which I have not investigated yet. I mean, if you wanted to look at those, that might be really interesting. Right. Well, in a few weeks here, I will have all the cards out on the table. You will know what I know about differential equations. At that point, you should have everything you need to start asking questions like, how can I modify it, if you want to try.
I mean, there wouldn't be much restriction in it trying to apply Laplace, really.
I don't know what it means.
All the necessary tools for that right now, right? I mean, if we're doing this integrating over here, why not do it for Laplace?
Right. Yeah, I don't know. You got to, starting point, you got to frame the question, and then you can try to answer it, I suppose. Hello. Not technically, but